We have seen how to calculate various matrix elements in perturbation theory, but let's see what we can do with those matrix elements. So eventually we will need to relate those matrix elements to something that is observable. And most of our observations will be based on, we will be measuring scattering cross-sections. Scattering cross-section, in fact, whatever we learn, whenever we do an experiment, it's actually a scattering process. For example, when you look at something, it is actually the photons from some source that is scattered from that object that you see. Or when you touch an object, it's the scattering of the charges making your hand and the object that you are touching that are scattering with each other, and then you are feeling the object. And so before calculating these scattering cross-sections, let's see from classical physics what is a scattering cross-section. Let's imagine that we have an object. This is our target. And we send some particles towards our target. So this is the probe or the beam. And this is let's just take the z-axis to be the direction of the velocity of our beam, of our probe. And this distance is called the impact parameter. And if they are interacting, the trajectory of the particle, which was initially horizontal, it will change and it will move in some different direction. And if we have a detector somewhere over here, this detector will see that the particle reaches this point. So the question is when we are sending our particle with some velocity, we are aiming at some area over here. So this is, let's just call it a very small angle, d sigma. And if we aim it right over here, it will follow this trajectory. If we slightly shift it above, in this case it will follow a trajectory which is very similar. It will probably deflect slightly less, but still go into our detector. If we send it slightly below, it will deflect a bit more, and it will still fall into a detector. So there is this area, d sigma, such that if our particle is aimed in that area, in that case my object will scatter and move into my detector. Now the detector is not really important, what is the detector. The important thing is that after the scattering process, the velocity of my particle, which is tangent to this line. Now the velocity of that particle is within this cone. Now such a cone we describe by a solid angle. So if you look at it from a far away distance, what you will see is this will be our target. This will be our particle or the probe. If we are at a distance much larger than b, it will be almost as if a collision will be almost head-on. It will be viewed as almost head-on. But the particle, after scattering, it moves in this direction. And when it is very far away, so this is the velocity vector will pass through the target. And this angle is what we call the solid angle. In fact, since our detector is over here, this cone is described by a solid angle, let's call it the omega. You see, before continuing, let's look at what we mean by angle and solid angle. If you remember the definition of the angle, it's defined on a circle. If you take any arc, this arc will see some angle. Let's call that angle theta. This arc has a length s, and the radius of this circle is r, then theta is s over r. So essentially, it's the direction, the angle essentially determines the direction in a unit circle. And you can just be more precise in your direction by just choosing this s to be smaller. So if an object is, by specifying your angle, you are specifying a given direction in 2 dimensions. The solid angle is the generalization to 3 dimensions. In 3 dimensions, we will take a sphere. And to specify a direction on this sphere from the center, what you do is you just specify some area. Specifying this area specifies the direction from the center. And if you imagine the cone with that area as your surface area, that is what we call our solid angle. And well, let me just use omega, it need not be small. If the area over here is A, solid angle is defined as A over R squared, R being the radius of this sphere. So here, the detector actually measures the solid angle. So there is an area, d sigma, near our target, such that if the object is targeted within this area, then we know that it will scatter into our detector. And what we are usually interested in is what we call the d sigma over d omega, the differential cross section. And this differential cross-section will contain the information about how our probe and the target interacts with each other. It will contain the information about the dynamics of this scattering process.